So up to this point, we've talked about unweighted and weighted DAGs for the single source short of path problem. And now we want to consider the most general case when we're allowed to have cycles, but not negative weight cycles. So why are negative weight cycles a problem? Well, if your goal is to compute paths, and you have a negative weight cycle, like maybe -5, 5, -3, then if you're considering walks instead of paths, well, you can just keep going around and around this loop. And every time you do, the weight of your walk is decreasing. So the total weight decreases by 3 every time you visit the cycle, or I should say complete the cycle. So this is a problem. Now, one way to avoid this problem is, well, instead of shortest walks, just consider shortest paths. Don't allow us to keep going around a cycle. The issue with this is that shortest paths are actually NP hard to compute. So, as Jeff mentions, the shortest simple path, which is the same as just a path in our terminology, is NP hard when there's negative cycles. And that's because there could be exponentially many ways for you to break cycles, and picking which one's the right one is just difficult. So that's why we focus on walks. In particular, when there's no negative weight cycles, the shortest walk will be a path. There's no benefit to reuse a node if it's not going to decrease your total value. And the only way it could decrease it is if it was a negative weight cycle. So the shortest walk will be a path when there's no negative weight cycles. In your graph. So since computing shortest path is NP hard, the best we can do is compute the shortest walk, and either it'll be -infinity, which indicates we have a negative weight cycle, or if there's no negative weight cycles, then it'll actually be the shortest path, which is what we want anyway. So to sacrifice is when there's a negative weight cycle, we can detect it and give up. But when there's not, can compute the shortest path. So this will happen if we focus on finding shortest walks. And so that's the main problem we'll look at. So the general case when there are negative weight cycles and we want to detect them, we'll talk about in lecture later. So we're just going to focus on computing when there aren't negative weight cycles, the solution. So it's going to be very similar to what we did here for DAGs. Now the issue here is now there's cycles in our graph. They're not negative weight, but they're still cycles. So even though that this recurrence is technically correct, we can never actually evaluate it because our dependency graph has a cycle, and so we need to loop forever. So we need to somehow limit the amount of looping. So the idea here is we need to limit the number of edges used in a path to avoid looping endlessly in a cycle. So we could get trapped in the cycle, but we want to avoid it. So we're going to use almost the same distance recurrence, but slightly change the problem we're solving. So instead, we're going to solve for distance at most I of v. And we're going to define this as the length of the shortest path, or technically it's a walk, but it will end up being a path, from S to V that uses at most I edges. Now, why is this useful? Well, at the end, we can return distance at most size of V minus 1 of V for all V, if we want the answer for every vertex, the distances. And the reason why is because any path has length at most V minus 1. This is because after you add one more in, you must be causing a cycle. Because by the pigeonhole principle, you have V minus 1 edges connecting V things, so that the second you add another one, you must have had a repeat. You already had V total things in your sequence. So if we allow at most size of V minus 1 things, then we know we're avoiding any kind of cyclic behavior. So that's enough iterations before we find the correct shortest path. We'll talk more about that later, but the key thing is we want to compute this, and that's something we can do with dynamic programming, which isn't too surprising because Bellman's the guy who invented dynamic programming. So let's try to solve this. So let's think of the base cases first, because those are actually pretty easy. So first, we have distance 0 if I equals 0 and V equals S. So if we're at the starting destination and we're not allowed to use any edges, then the answer is 0. Notice this is an and not an or. And that's because you can start at S and get back to S in negative amounts by taking more edges. So in fact, this is only true when both of these conditions are true. If I was greater, maybe I is at least 2, well, maybe you could have S, leave S, -2, come back for +1, so actually get a walk of size -1. So that's an example of why we have this particular base case. The other easy base case is infinity, and this is when I equals 0 and V is not S. So if we ran out of the number of edges we're allowed to use, but we're not at the source, well, definitely we do not have a path from S to S. We have a path from V to V, which does not include S. So in that case, there is basically no distance that we can quantify, and so we just make that infinity. Otherwise, we have a decision. Either we can just remove one of the edges. So one option is we just recurse on I minus 1, the same V. So this is saying, essentially we're going to skip this turn. We don't really need I minus 1 edges, so we're just going to ignore the last edge. So either we ignore the last edge and recurse, or we find the best last edge, just like in the previous recurrence. So now the difference is, when we recurse, we have at most I minus 1, because we just used up one of the edges. Otherwise, it's basically the same. So that's the recurrence. The main difference, again, if we look at this one, is here we always pick the best last edge and recurse. Whereas here, because we have this limit on the number of edges, we can either pick the best last edge and use up one of our options, or we can simply just skip. We don't need to use the last edge. We just recurse with a smaller number of edges. So you might be thinking, why would you want to do that? Well, maybe you're thinking of a case where you start at S, you can leave S, and come back to S, but it's actually cost 4, where you'd prefer to just stay at S and get 0. In that case, you want to keep using up your edges. So you keep, say I is 3, where you're going to keep decreasing it and recursing on dist 2 and then dist 1 until you hit dist 0. And dist 0 gives you the option to get just 0 out. So there are cases when you actually benefit from not using any edges. But ultimately, this is just an artifact of the way we've defined the subproblems. So that's the recursive equation. Now the question is, what are the subproblems, what are the dependencies, etc.? Well, clearly there's dependencies on smaller values of I and edges and nodes, or let's say, and successors or predecessors. So these are the key dependencies. We have a subproblem for each V and I. Let's use orange. And they depend on smaller values of I and predecessors of V. So if we drew like a little graph here, if this was V, then we need to know these values first. I'll call this C. So we need to know, before we compute V, we need to know U and Z for all smaller values of I. And so naturally, what we're going to do if we need these nodes to come first is to use a topological order. So the eval order is going to be a topological order. So recall in class, we typically use a reverse topological order, which is a post-order traversal or a DFS. But here we're actually using a true topological order because we're starting from the source and branching out instead of starting from the sink and going towards it. So we do a topological order for the vertices, and we will evaluate I from the largest value down to the smallest. Actually, that's backwards. So here I is also increasing. So we need smaller values first. The base case is I is 0 and it goes up to V minus 1. So that's our eval order. And the last step is to look at running time. So what's the running time of this algorithm? Well, I can take possibly V values, and the inner loop stuff is going to loop over all successors of or predecessors of V. So overall what we have is for each I, we have a sum of U, of degree of U, plus some extra stuff. So overall, this is going to be, we have size of V values of I, and that sum is going to be proportional to the edge list. So something like this, which is O of V times E. Okay. Now note here that technically what we get is size of V squared plus the size of VE, but generally we're assuming that the size of E is proportional to the size of E squared anyway, And so this basically just becomes like a constant factor in front. So if you're wondering why there's like no v there, it's just because we're upper bounding it by e. And so that's why we get this running time.